All right, well, exponential is probably one of the most misused words in math, right? We look at any curve that is getting steeper and say that it seems to be increasing exponentially, right? If we were to look at x squared's graph, I'm just going to draw a nice little sketch of it. That's better. Okay, and if we look at this curve, we're like, oh yeah, this curve is increasing exponentially because it is getting steeper, but it's not increasing exponentially. This is a quadratic function, so it's increasing quadratically. So exponential doesn't just mean that a function's getting steeper, right? And we want to pin down what it actually means to be exponential. So first, let's talk about what it means to be quadratic. So what we're going to do is look at how much the outputs are changing by as the run increases by 1. So I'm going from 1 to 2, 2 to 3, 3 to 4, 4 to 5. My run is going up by 1. How much is my rise going up by? So what is it from 1 to 4? Okay, you should copy this table and do this with me. What is it from 1 to 4? What is it from 4 to 9? What is it from 9 to 16? What is it from 16 to 25? Okay, it's 3, 5, 7, and 9. So then this is the change in rise compared to the change in run. So now what if we take the change and the change in rise? What if we take the difference of the difference? Well, what do we get? We get 3 to 5 is 2, and we get 2 to 5, or 5 to 7 is 2, and 7 to 9 is 2. So our second layer of looking at the change in rise, so the change in the change in rise, is linear. And this is in fact true for all quadratic functions, right? It's a degree 2, so the second layer is linear. Let's see if this extends to cubics. So once again, copy down this table and do this with me. We're going to look at the change in rise as my run increases by 1. So my change in rise is 7, 19, 37, and 61. All right, let's go one layer further and look at the change in the change, the difference of the difference. Okay, so that gives me 12, 18, 20. So now my third layer has a difference of 6 and a difference of 6, right? So my third layer is now linear, all right, and this is a cubic. So let's keep going and see if this extends to a x to the fourth function. If this were to work, then the fourth layer should be a linear layer. So we'll do the difference, and then the difference of the difference, and then the difference of the difference of the difference, and then hopefully after that we will see a linear pattern. So first, the first layer, there's our differences, 1565, 175, 369. Our second layer, 50, 110, 194. Our third layer is 60 and 84. So this is the layer where now if we take the difference, it should be linear, but we don't have enough values on our table. So no, not to worry, let's just add one. I'm going to add x equals 6. So x equals 6, there's the output. Okay, so then 625 to 1,296 is 671. And then the difference from 369 to 671 was 302. Difference from 194 to 302 is 108. And now we have a difference of 24 and a difference of 24. So the fourth layer is linear. And this is a degree 4 function. So with all polynomials like this, where we have a degree, okay, that degree will tell us how many layers we have to go when looking at the change in rise to get to the linear layer. And we will always hit the linear layer with a polynomial. Okay? And this should not surprise you. This is related to the derivative because the change in rise over the change in run, as we've always talked about, is just the slope. And that's what we're really looking at, right? Is change in rise divided by the change in run, where in this case the change in run is just always 1 on these tables, right? And then we're looking at that, how that compares to the change in rise. So the only part of this table that never mind, you should look at this whole table, right? So we have x squared, and we talked about how we had to do 2 layers of looking at the change in rise before we hit the linear piece, and that linear change was 2, right? Let's go back to x squared real quick. Oh my gosh, I have to go so far back. Okay, so remember that the difference was 2, right? 2, 2. Okay, well, the derivative of x squared is 2x, so that seems to be connected. So we have this table where the derivative is 2x. Okay, now if we looked at x cubed, remember we had to go 3 layers before we hit the linear piece, so we took if we take the derivative, and then all this means is we're taking the derivative of the derivative. What's the derivative of 3x squared? Oh, that's 6x, right? And if we go back to that x cubed table, remember we did the difference and then the difference of the difference, and then the third layer, the difference of the difference of the difference was 6, and our linear derivative that we hit with x cubed, if we take the derivative and then the derivative of the derivative, is 6x. So again, it seems like those are related. And when it comes to these tables, just copy down this piece and then this piece, right? So for this next one, you're only going to worry about this one and this one, right? Oh my gosh, but I could do a better job of circling those. This one and this one, okay? So with x to the fourth, we take the derivative, we get 4x cubed. Take the derivative again, we get 12x squared. Take the derivative one more time, we hit 24x. And again, that's what we saw with x to the fourth. We take the change in rise, and then if we take the difference of that change in rise, so the change and the change in rise, and then the change and the change and the change in rise, what do we get now? We get that that linear piece is 24, okay, seems to be related to our derivatives, okay? So, what about exponential functions, like a function like 2 to the x? So the first thing we're going to do is we're going to fill in this table. So we're going to do x equals 1, and then 2 to the 1 is 2. And then we're going to do x equals 2, and then 2 to the 2 is 4. I'm going to go ahead and let you do the rest of these. Okay, pause the video and try it out. Okay, here's your table. So our next step is to take the difference of, we're going to do the change in rise. So 2 to 4 is 2, 4 to 8 is 4, 8 to 16 is 8, 16 to 32 is 16, 32 to 64 is 32, 64 to 128 is 64. Okay, well, let's do the change and the change. Okay, 2 to 4 is 2, 4 to 8 is 4, 8 to 16 is 8, 16 to 32 is 16, 32 to 64 is 32. Okay, so we're now 2 layers. Let's go again. Let's do the change and the change and the change. 2 to the 4 is 2, 4 to the 8 is 4, 8 to the 16 is 8, 16 to the 32 is 16, 2 to the 4 is 2, 4 to the 8 is 4, 8 to the 16 is 8. Okay. So you can see that this is pretty much just a repeating pattern. And so it should be reasonable to say that if we just keep going, we're going to go forever and ever and ever, and we're never going to hit the linear piece. So this is what it means to be exponential. Okay? Not only is our function getting steeper and increasing, but if we keep taking the difference and the y value, which is that vertical value, and we keep going layer by layer by layer, we're never eventually going to hit a piece where the change is linear. It's always going to continue to be double each time. 2 to 4, 4 is double 2, 8 is double 4, right? 32 is double of 16, 16 is double of 8, 8 is double of 4. So exponential functions are increasing at like a different level than other functions. They're getting steeper, and each of their derivatives is also getting steeper. Each of their derivatives is exponential. With polynomials, if we continually take a derivative, eventually we're going to at least hit a linear piece, right? Because if we take the derivative long enough, we'll eventually hit part where it's x to the first power, because we're continually subtracting 1 from the exponent by using the power rule, right? That's never going to happen with our exponential function. We're never going to hit a derivative down the line that's going to be linear. They're all exponential, okay? Never hit the linear layer. Okay, so we're just going to skip that. Okay. Cool. We're going to just skip to the next part of the video instead of doing more practice, but you will have problem set problems where you will have to determine what type of function is represented on a table by taking the difference in the y values until you hit the linear piece, right? Or if you determine you're never going to hit a linear piece, that would be exponential, right? Okay. So this is the second part of the video where we're going to talk about the idea of compound interest, okay? So let's say I have $100, and let's say I find a way to invest that $100 so that my investment increases by 2% every month. That would be an insane investment, by the way. If you found that kind of increase every month, you would really make money fast. So the question is, how much money will I have after 12 months? Well, first we should figure out how much we're increasing by, right? So if I'm increasing by 2%, well, what is 2% of 100? Okay, 2% of 100 is just equal to 2, right? So I'm gaining $2 in that first month by gaining 2%. So your brain might think that after 12 months then, I'm just going to gain 12 times 2, which is $24, okay? But that is not exactly right, because interest compounds, right? Meaning that in my first month, I'm going to get 100 times 0.02, so I'm gaining 2%. So as we learned in class today, I should make this 1.02, right? To show that I'm gaining. And that's going to give me, I now have $102, right? So that interest now compounds, and now my amount is 102. And now that's going to gain 2% next month, right? So now I'm going to do 102 times 1.02, right? And I'm going to see what I get. And in fact, the function I'm going to use is just 100, my initial value, times 1.02. And if I want to know how much I'm making after 12 months, I'm just going to raise this to the 12th power. And let's go ahead and use a calculator and figure out what that should be. Okay, so it turns out this actually ends up being about 126.82, okay? So that may not seem like a big difference from 20. So we said, like, it's not going to be 24. It's going to be more than that since the interest is compounding. It ends up being 126.82. So in my first year, in my first 12 months, I made $26.82 on my investment. I increased my 100 to 126.82. So then what happens in the second year? So let's say I do this for 2 years instead of 1 year. So I do 1.02 raised to the 24, right? So I only made $26.82 in that first year. Let's see how much I make if I go for 2 years. I'm now to $160.84. Okay, so now I've gained $34 from my first year to my second year and a total of $60.84. Okay, let's do one more year. Let's do 100. Oh my gosh, that looks like a 6. 100 times 1.02 raised to the 36. Let's see how much we make in 3 years. So we'll do 100 times 1.02 raised to the 36. And now that is equal to 203. And we're going to round this up to 99. So basically 204. So now we've gained another $43, right? So first we gained 26, then we gained 34, and then we gained 43. And this is only in 3 years. You can see how over time this investment is going to continue to grow exponentially. So that's the idea of compound interest. It compounds every single month, which means that the amount that I'm gaining every single month is going to continually go up. So I'm gaining the 2% interest, but what that 2% is going to increase because we're applying 2% to a larger value, and that's what you really need to understand. So compound interest example. So we're going to talk about 100% interest first. So obviously if I have $1 and I gain 100% interest on that dollar for a year, then I'm going to have $2 at the end of the year, okay? Now this is how you're going to get confused by financial problems, okay? Because they're going to say something like, we'll give you 100% interest, but we're going to compound it twice. So what does that mean? It means that we're going to get 50% interest after 6 months, and then we're going to apply 50% to that at the end of the year. So after 6 months, I'm going to get 50% of what I started with. So now I have $150, right? Because I started with $1. I'm going to gain half of that as interest, so now I'm at $150. So now I'm going to apply when I apply this interest again, I'm going to go ahead and apply that 50% to what I have. So now I have $150, and I'm going to gain 50% of $150, which now puts me at $225. So that 100% interest, because 50% plus 50% is 100, actually ends up being 125% gain since I'm compounding it twice. I'm splitting it up into 2 groups, and then I'm applying those amounts twice. Okay. So here's our general compound interest formula. Okay, so let's just do an example. Let's say I have 50 times 1 plus 0.04 over 2 raised to the 2 times t. So this 50 is just my initial amount. I'm starting at $50. This blue part means that I'm going to keep at least what I started with. I have 100% of that, which is 1, right? 1 as a percentage is 100%. And then I'm going to gain 4% interest, but we're going to compound that twice. So I'm going to do 4% interest, but I'm going to divide that interest by 2, and then I have to apply it twice per year since I'm compounding it twice. Okay, so this is our example. We have our initial amount, we have our 100% plus however much we're gaining, divided by however many times we're compounding it, raised to the 2t. So how this might be written would be P of t equals P naught, where this is the initial amount, times 1 plus our interest rate divided by n to the n times t. So this is percent interest as a decimal. Okay, this is our number of compounding, which also shows up right there into the t. Okay, this is our unit of time, which is usually years in problems like this. And then this is our initial amount, which we just call P naught. Okay, so let's, and again, pause the video please to get this down. I'm moving fast, so you should pause when needed to get caught up on your actual notes, okay? So, our practice, we have a starting amount of $30. We're going to gain 5% interest compounded quarterly, which just means we're going to do it 4 times. And I want to determine how much that money is going to be worth after 3 years. Okay, so let's figure this out. We have P of t equals 30 times 1 to represent that we're keeping at least that 30 amount, and then we're going to add some. We're going to add 5%, 0.05, divided by 4 compoundings, raised to the 4 times t to make sure that we're applying that interest 4 times. And this particular question is asking for how much we're going to have after 3 years. So I should do P of 3, which is equal to 30 times 1 plus 0.05 over 4 raised to the 4 times 3. And so we should just type this into a calculator now. 30 times 1 plus 0.05 divided by 4. And then we're going to raise that to the 4 times 3, which is 12. And we now have $34, and this is going to round down to 82 cents. Okay, so $34.82 is our amount. Okay, so that's another example that you can work from. You also had this example that we started with when we introduced this function. And so now you have a closure to do. You have 2 problems, and you should do these in your notes and then submit pictures to Google Classroom when you are done.